So now we're going to talk about how to analyze turbo machinery. Um, how we're going to model it, how we're going to study it. So it won't surprise you that pump and turbine flow is almost always very complicated. You've got these spinning blades, you've got pistons moving in and out, all kinds of stuff going on, and that's usually going to involve lots of viscous forces in the flow. Usually going to have flow separation regions. You're going to have turbulence. All those things are going to happen inside a pump. And we're going to ignore all those things. So basic turbo machinery analysis, if you're just going to do some, try to understand and model pumps, people assume that the flow is inviscid. So inviscid, of course, means no viscous effects. So that's completely wrong. But it allows us to, understand what's going on in the pump and to begin to estimate how much power would be needed or what kind of pump we would need. And then, of course, as always, people use experimental results to handle the fact that it's not really like this, that it's not truly inviscid at all. In fact, we know it's going to be nothing like that. But the fact that we treat it as inviscid means, of course, that we can use our friend, the Bernoulli equation. So again, we've talked about this many times, the Bernoulli equation. Some people only seem to think fluid mechanics is the use of the Bernoulli equation. That is always an approximation. It's always untrue. But once again, we can use it to understand what's going on. And in this case, really get some practical results, even though you do have to understand that there are going to be friction losses in addition to whatever you calculate. All right, so we've got the Bernoulli equation here, and we'll put it in for the inlet and the outlet. So there it is. With Bernoulli, if no pump were happening, if there were no pump or turbine, this is what would be true. Right? If this would be this would be true if nothing were happening. So if the went through the system, there were no pump and no turbine, then according to Bernoulli, they should be equal to each other because they're just equal to some constant that doesn't change. Notice we only have one density here because we are assuming still incompressible flow. So we'll do incompressible flow. Of course, there are many pumps and propellers and things where you'd have compressible effects. We're not going to be dealing with those. That's beyond the scope of this course. So we'll have incompressible flow, in which case we have these two things being the same if you had no pump or turbine. Of course, what the pump and the turbine are going to do is they're going to change the amount of energy in the flow. We saw that the Bernoulli equation came right out of conservation of energy. So we're going to now characterize that change by a number, which we're going to call the head. So it's going to be the net head is going to be the main parameter that we use in pump analysis, net head, and its symbol is big H. And the definition of the net head is exactly this change that we just indicated was going to happen if you had a turbine or a pump. So I'm going to P out over rho G. I'm just dividing everything by rho G because that's what people do for calculating head pressure and head energy. And so Z out here, and then minus everything in there. So there's going to be a difference if you have a pump or a turbine. There is going to be a difference between this group on the outlet and this group at the inlet. Bernoulli says there wouldn't be a difference if no energy were taken out of the system or added to the system, but that's exactly what pumps and turbines do. They either take energy out or add energy in. So these values are going to change. Notice that we have this is a height. So H is for head, but the reason is because people think of this as the amount of height. So notice the Z terms aren't being multiplied or anything. So this is actually going to be the units of this thing are actually height. So it's basically it's the equivalent, like if you think of it as a pump, it's how high could this pump whatever the fluid is, given the fluid has this density. So that's what this is saying. Or if you extract, fluid, if you're extracting energy, how much energy is if that fluid had fallen down a certain height, come down a certain height. So that's what head pressure is, and this head that they use, this net head. So as I said, H really you can see is a measure. It's really related to Z out and Z in here. And what the net head is defined formally as H is equal to HS minus HF. And so HS is the head supplied by the pump. And HF is all that stuff that we just talked about that we were basically going to ignore. So it represents the losses in the actual pump. So we can calculate, how hard the pump is working or how much energy, it should be supplying to the fluid. And then, it's not going to, the amount of change we see in these parameters is not really going to equal that because it's going to lose something due to losses, which are signified by HF. So this is just, F is losses in the actual pump, which are primarily due to friction. There's friction, of course, in the liquid because there's turbulence and spinning and all kinds of frictional effects. And there's also friction in the pump itself. So there may be friction in both, all of which, we can account for here. For many pumps and turbines, Z in and Z out are approximately the same, right? So that's very common. That's really common. It's actually pretty unusual that the pump itself has a significant height change or the turbine itself has a significant height change. And it's also true that for many of these pumps and turbines, the velocity in and the velocity out are not very different. So in those cases, you're really just looking at pressure changes. So people, for many, many pumps, for these conditions, we can calculate that net head as being approximately just equal to P out minus P in divided by rho G. So that's a formula that is commonly used for turbines and pumps where you just don't have significant changes in Z. I say that's almost always true. And don't have a significant change in velocity. Again, almost always true. There are situations, of course, where you really are changing the velocity of the fluid in a significant way. But if you think about lots of turbines and fans, you're not going to have a big change many times in those velocities. So sometimes you do. If you're expanding steam, for instance, the steam can expand as it goes through the turbine. It can come out with a much higher velocity than it enters. But by mass conservation, unless something like that happens where its density changes a lot, you're not going to have a big change in velocity usually, because otherwise, how would that conserve mass if it's coming in a lot faster than it's leaving? It could be coming in a small pipe and leaving in a large pipe. That kind of thing could change velocity as well. So there are ways it can happen. But since we're dealing with incompressible flow, the most common way that these velocities matter is when the gas or something expands dramatically. And of course, that wouldn't be incompressible. So that wouldn't really happen. So in a lot of cases that we're going to be studying for incompressible flow, this is a good explanation. So this is a good description of the net head pressure. So this is for incompressible situations, incompressible flow, where Z in is approximately Z out, and V in is approximately V out, like it says right there. So we'll just circle that. So if that's the case, then you can use this, and obviously that's pretty simple. We can relate the net head directly just to the pressure change of the fluid.